The concept we'll discuss in this video, the cumulative distribution function, is actually useful both in the case of discrete random variables and continuous random variables. For the case of continuous random variables, it's especially nice because it will give us a way of calculating probabilities without having to use calculus. Let's begin with a PDF, a probability density function like we've seen before. This is for a uniform random variable, much like the one in the pipe example, but this one takes values between 15 and 25. And notice that the height is 0.1. This is so that the area under the curve is equal to 1. Now I'm going to express the same information on the right-hand side in a different way using the cumulative distribution function. Notice that this has the same range 15 to 25 with an upward sloping line between these two values that ends at 1. This is because the CDF, often denoted capital F of little x, tracks the probability that capital X, meaning the random variable, is less than or equal to any little x that you might care to plug in. This is the idea of a cumulative distribution, probability up to the point little x. Let's see this graphically. So on the left-hand side, I express probability as area, and on the right-hand side, the corresponding probability is equal to the height. And as I accumulate more area moving to the right along the x-axis, the height increases, reflecting the fact that there's more area cumulatively to the left of the point x. So here's the final height. And this is useful for doing calculations. So for example, let's say that I'm interested in the probability that the random variable x is less than or equal to the value 17. So on the right-hand side, we can do this by calculating the area of this rectangle. This is the height, 0.1, times the difference in the end points of the range, which is just equal to 0.2. Now on the right-hand side, I can do the same calculation if I know the height at the point 17. So let me give you the analytical expression for the graph that you see. This is capital F of x is equal to 0 for any value x less than or equal to 15. It's equal to this line x minus 15 over 10 for any values between 15 and 25, and it's equal to 1 for anything greater than 25. So now that you have the math behind this picture, we can take the value 17 and plug it in and get 17 minus 15 divided by 10, or 0.2. Notice that this is the same as on the left-hand side with the PDF. Let's do a more complicated calculation now. The probability that x is now in between 16 and 21. We know how to do this on the right-hand side. Again, we'll calculate the area, height times the difference in the endpoints of the range, and this is 0.5. Now on the right-hand side, using the CDF, we'll do a little bit of a trick to be able to use this function. This isn't exactly in cumulative distribution form, but we can notice that this probability is exactly just the probability that the random variable is less than or equal to 21 minus the probability that it's less than or equal to 16. So first we take all the mass that's less than 21, but we subtract off again the mass that's also less than 16. Here's the formula again, and now I'm plugging in two values, 21 and 16, and subtracting the two to get 0.5, again just like on the left-hand side. Now in this case with the uniform random variable, you might think that the CDF calculations are actually more complicated than the PDF calculations. You're probably right here, but think about the normal distribution or another distribution that has a much more complicated probability density function. In this case, if you can just have a formula or numbers to plug in for the CDF, it's a lot easier than having to calculate areas as we did here. Now, before we finish, let me just give you a summary of the properties of the cumulative distribution function.